Hi, Stu Schwartz from MasterMathMentor.com. This is video BC24. The topic is Power Series and it covers the BC Manual pages 116 through 119. A number of chapters ago, we introduced the idea of approximating functions by its Maclaurin and Taylor polynomials. For example, we showed that f of x equals e to the x can be approximated by its Maclaurin polynomials. The first degree polynomial is e to the x is approximately equal to 1 plus x. The second degree polynomial was e to the x is approximately equal to 1 plus x squared over 2. We move to the third degree polynomial, which is e to the x is approximately 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And finally, we move to the fourth degree Maclaurin polynomial. E to the x is approximately 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. When we studied this, we did not have the knowledge of infinite series, which means that our polynomials had to stop somewhere. But now we see that this and other functions can be represented by a specific infinite series called a power series. The power series for e to the x would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus plus x to the n over n factorial plus and that can be written as summation n equals 0 to infinity of x to the n over n factorial. What is more important is that this series converges for all real numbers x, allowing calculators or computers to calculate e to the k, where k is a constant, to extreme accuracy by using the power series. So let's now define a power series. If x is a variable, then an infinite series in the form of summation n equals 0 to infinity of a sub n x sub n is called a power series centered at x is equal to 0. And when expanded, this is a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus plus a sub n x sub n plus . We can always also have a power series centered at some constant x is equal to c. And that would be written as summation n equals 0 to infinity of a sub n times the quantity x minus c raised to the n power, which is a sub 0 plus a sub 1 x minus c plus a sub 2 quantity x minus c quantity squared plus a sub 3 quantity x minus c quantity cubed plus plus a sub n quantity x minus c raised to the nth plus . It should be noted that for definition purposes, we will define 0 to the 0 as 1. In the first three problems, you are given an infinite series. You are to expand the series and decide whether it is a power series, and if so, determine its center. 1 is summation n equals 0 to infinity of x to the n over n plus 1 factorial. Expanded, this is 1 plus x over 2 factorial plus x squared over 3 factorial plus x cubed over 4 factorial plus . This is a power series in that there is a constant, an x term, an x squared term, etc. And its center of convergence is x is equal to 0. Number 2 reads summation n equals 0 to infinity of negative 1 to the n times the quantity x minus 1 to the n. Expanded, this is 1 minus quantity x minus 1 plus quantity x minus 1 quantity squared minus quantity x minus 1 quantity cubed plus . This is a power series in that there's a constant and an x minus 1 to the first power, an x minus 1 to the second power, etc. This is a power series that will be centered at x is equal to 1. 3 reads summation n equals 0 to infinity of n over x to the n. This would be 0 plus 1 over x plus 2 over x squared plus 3 over x to the third plus dot dot dot. This is not a power series because we need in a power series a constant, an x term, an x squared term, an x cubed term, and we do not have that. Several facts about power series. All power series in the form summation n equals 0 to infinity of a sub n times x minus c raised to the n power converge at c, which is called the center of convergence. The domain of a power series, the set is the set of all x values for which the series converges. Our job will be to find this domain of a power series. If we look at the first problem, summation n equals 0 to infinity of x to the n over n plus 1 factorial, this will converge at the center, x is equal to 0. When x is equal to 0, our series is 1 plus 0 plus 0 plus 0 plus dot dot dot, which is equal to 1. And of course that means it converges. X is equal to 1 is in the domain of the series by the ratio test. If we look at the series 1 over n plus 1 factorial, we can use the ratio test to show that that will be convergent. If we look at summation n equals 0 to infinity of negative 1 to the n times x minus 1 raised to the n, that too converges at its center, x is equal to 1, and we will end up getting 1 plus 0 plus 0 plus 0 plus dot dot dot, which is equal to 1. But x equals 0 is not in the domain of the power series by the nth term test. If we look at the limit as n approaches infinity of negative 1 to the n times x minus 1 to the n, we will find that that is not equal to 0. What interests us is what values of x make the power series converge, which of course means that the series reaches a finite limit. There are 3 possibilities for values of x for which the power series converges: at a single point c, at an interval about c, or the entire number line. As stated before, it is obvious that a power series always converges at its center. There are 3 possibilities to determine the radius of convergence r, as shown in the picture. First, we can have convergence at a single point, which is the center of convergence. If that is true, then our radius of convergence r is 0. Second, our series can converge at C and all points around C within some interval. In that case, we will say that r is a constant, and that is why we call it the radius of convergence. It's sort of like the radius of a circle. Any values to the r units to the left of C and r units to the right of C will cause convergence. Finally, if our series converges at C and all values of x, then we will say that the radius of convergence r is infinite. Problem 4 asks to find the radius of convergence of the series summation n equals 0 to infinity of n plus 1 factorial x to the n. Expanded, we find that that is 1 plus 2x plus 6x squared plus 24x to the third plus dot dot dot. This is clearly a power series as it has a constant, an x term, an x squared term, etc. And it certainly converges at the center, because if x is equal to 0, then the summation n equals 0 to infinity of n plus 1 factorial x to the n is simply 1 plus 0 plus 0 plus dot dot dot, which is equal to 0. So it converges at the center. The question is, does it converge at any other value of x? For instance, let x equal 0.5. Then summation n equals 0 to infinity of n plus 1 factorial times x to the n would be 1 plus 1 plus 1.5 plus 3 plus 7.5, and that fails the nth term test, and it is clearly divergent. We have to use a convergence test to look for convergence. Since it has factorials, the ratio test is used. We look at the limit as n approaches infinity of the absolute value of the n plus first term over the nth term. And that is the limit as n approaches infinity of the absolute value of n plus 2 factorial x to the n plus 1 over n plus 1 factorial x to the n. And that is the limit as n approaches infinity of the absolute value of n plus 2 times x. And that is infinity. Meaning that there is no non-zero value of x making the limit less than 1. So summation n equals 0 to infinity of n plus 1 factorial x to the n is divergent at all values except at its center, x is equal to 0. And therefore its radius of convergence, r, is equal to 0. For the power series, summation n equals 1 to infinity of negative 1 to the n plus 1 times x to the n over n factorial, which expands to x minus x squared over 2 factorial plus x cubed over 3 factorial minus x to the fourth over 4 factorial plus dot dot dot. We would like to find the radius of convergence r. As do all power series, this power series converges at the center, as if x is equal to 0, then summation n equals 1 to infinity of negative 1 to the n plus 1 times x to the n over n factorial is 0 minus 0 plus 0 minus 0 dot dot dot, and that is equal to 0. The question is, does it converge at any other value of x? For instance, let's let x equal 1. Then summation n equals 1 to infinity of negative 1 to the n plus 1 times x to the n over n factorial is 1 minus a half plus a third minus a fourth plus dot dot dot. And we know that to be a convergent alternating series. So it converges at x is equal to 1. Are there any other values where it converges? Again, because of the factorial, we will use the ratio test to check for convergence. We look at limit as n approaches infinity of negative 1, x to the n plus 1 over n plus 1 factorial, divided by x to the n over n factorial, which is multiplying by n factorial over x to the n. And that becomes the limit as n approaches infinity of the absolute value of negative x over n plus 1. And we know that has to be less than 1. But since that limit is equal to 0 for all values of x, then all values of x make that limit less than 1. So summation n equals 1 to infinity of negative 1 to the n plus 1 times x to the n over n factorial is convergent at all values of x, and therefore its radius of convergence r is equal to infinity. The first two examples were all or nothing affairs. While they were both convergent at the center, one of them was convergent nowhere else, and one was convergent everywhere else. Let's look at an example that is convergent on an interval. Number 6 reads, summation n equals 0 to infinity of 4 quantity x minus 2 raised to the nth power. When expanded, this is 4 plus 4 times quantity x minus 2 plus 4 quantity x minus 2 quantity squared plus 4 times x minus 2 quantity cubed plus dot dot dot. We know our power series will be convergent at the center, x is equal to 2. Summation n equals 0 to infinity of 4 times x minus 2 raised to the nth, if x is 2, is 4 plus 0 plus dot dot dot, which is 4. So it converges at x is equal to 2. Does it converge anywhere else? If x, for instance, is 2.5, then our series, summation n equals 0 to infinity of 4 times x minus 2 to the nth power is 4 plus 2 plus 1 plus 1/2 plus dot dot dot, and that is a convergent geometric series. So the question is, what are the range of values where our series is convergent? We will use our geometric test. The absolute value of x minus 2 is less than 1. So that means that x minus 2 is less than 1, and negative quantity x minus 2 is less than 1. So that implies that x is greater than 1 and x is less than 3. Since the center of convergence is 2, then r is equal to 1, and the interval convergence, which is the interval of all values of x where our series converges, is from 1 to 3. We cannot graph a power series because it has an infinite number of terms. We can graph, though, polynomials of partial sums, one with one term, two terms, etc. Here we show partial sums of 1 to 5 terms in different colors. Notice how the graph rushes towards infinity or negative infinity outside the radius r of 1 about x is equal to 2, meaning to the left of 1 and to the right of 3. There is a fine line between convergence and divergence. For instance, let's look at the term when n is equal to 1000 and x is equal to 2.99. The term that is added is 4 times the quantity 2.99 minus 2 raised to the thousandth, and this is equal to approximately 0.00017. So we are adding very little onto the sum of the series. However, when our value of x is just outside the interval of convergence at 3.01, the term we are adding is 4 times the quantity 3.01 minus 2 raised to the thousandth, and that's 83,837. So it's clear that we're adding huge terms and this will diverge. So the line at x is equal to 3 is a very, very fine line. Let's expand the series summation n equals 1 to infinity of x over 5 raised to the 2n minus 1 and find the radius and interval of convergence. First, the expansion, summation n equals 1 to infinity of x over 5 raised to the 2n minus 1 is x over 5 plus x cubed over 125 plus x to the 5th over 3,125 plus dot dot dot. This power series obviously converges at the center, x is equal to 0. The question is, does it converge at any other values of x? For instance, if x is equal to 1, we have summation n equals 1 to infinity of x over 5 to the 2n minus 1. And when x is 1, that becomes 1/5 plus 1/25 plus 1 over 3,125. And that's a convergent geometric series. So it converges there. What about other values? While we could use the geometric test, we will use the versatile ratio test. The limit as n approaches infinity of the n plus first term over the nth term is the limit as n approaches infinity of the absolute value of x over 5 raised to the 2n plus 1 over x over 5 to the 2n minus 1. And this becomes the limit as n approaches infinity, the absolute value of x squared over 25. And that has to be less than 1. Meaning that plus or minus x over 5 has to be less than 1, and x has to be greater than negative 5, and x has to be less than 5. So since the center of convergence is 0, the radius of convergence is 5, and therefore the interval of convergence is from negative 5 to 5. Our results are confirmed by graph. We look at the first, third, fifth, and seventh degree polynomials for the series, and we see that the graphs with various number of terms rushes towards infinity or negative infinity outside the radius r of 5, about x is equal to 0. The problem we face now is that the method we just showed says nothing about the convergence of the series at the endpoints of the interval of convergence. For the series that has a radius of convergence r not equal to 0 or infinity, there are 4 situations that can occur. The series can converge at the left endpoint, right endpoint, both endpoints, or neither endpoint, as illustrated by the figure on the screen. So once we determine the radius of convergence r, we must check out convergence at both the left and right endpoints. On number 8, we are given the series summation n equals 1 to infinity of x to the n over n plus 1. We would like to write the first few terms of this series and then find the interval of convergence. This series, when expanded, is x over 2 plus x squared over 3 plus x cubed over 4 plus x to the 4th over 5 plus dot dot dot. This power series converges at the center, x is equal to 0. To find the radius of convergence, we'll use the ratio test and look at the limit as n approaches infinity of x to the n plus 1 over n plus 2 times n plus 1 over x to the n. The n's drop out and we're simply left with the limit as n approaches infinity of the absolute value of x, and that has to be less than 1, meaning that x has to be greater than negative 1 and x has to be less than 1. We now check out the endpoints. If x is negative 1, then our series expands to negative 1/2 plus 1/3 minus 1/4 plus 1/5 minus dot dot dot, and that's an alternating convergent series. If x is equal to 1, our series turns to be 1/2 plus 1/3 plus 1/4 plus 1/5 plus dot dot dot, and that's the harmonic series, which is divergent. So our interval of convergence is the interval -1 to 1, where -1 it is included and 1 is not. This is borne out by the graph. We examine polynomials containing just the first term in red, the first 2 terms in purple, the first 3 terms in blue, and the first 4 terms of the series in green. All of them diverge outside x is equal to 1 and x equals -1. But notice that around x is equal to 1, they start to diverge to infinity much faster than around x is equal to -1. That is because the series is still convergent at x is equal to -1, while at x is equal to 1, it is divergent. 9 is the summation n equals 1 to infinity of quantity x minus 1 to the n over n squared. We would like to expand it, find the radius and interval of convergence. The series expands into x minus 1 over 1 plus quantity x minus 1 squared over 4 plus quantity x minus 1 cubed over 9 plus dot dot dot. The power series converges at the center, x is equal to 1. We check out using the ratio test any other convergence, and we look at the limit as n approaches infinity of x minus 1 to the n plus 1 over n plus 1 quantity squared times n squared over x minus 1 to the n. And that is the limit as n approaches infinity of the absolute value of x minus 1, and that has to be less than 1, meaning that x has to be greater than 0 and x has to be less than 2. We then check out the endpoints. When x is equal to 0, our series is negative 1 plus 1/4 minus 1/9 plus 1/16, and that is an alternating series that converges. When x is equal to 2, our series turns out to be 1 plus 1/4 plus 1/9 plus 1/16, and that is a p-series that also converges. So the interval of convergence is the closed interval 0 to 2. This is borne out by the graph. We examine polynomials containing just the first term in red, the first 2 terms in purple, the first 3 terms in blue, and the first 4 terms of this series in green. Notice that, unlike the last problem, just outside x is equal to 0 and x is equal to 2, the series appears to be diverging at roughly the same rate. Good evidence that both x is equal to 0 and x is equal to 2 are in the interval of convergence. Number 10 reads summation n equals 0 to infinity of negative 1 to the n times the quantity x plus 2 raised to the n over 3 to the n. We'd like to expand the expression and find the radius and the interval of convergence. We first expand the expression and write this as 1 minus x plus 2 over 3 plus x plus 2 quantity squared over 9 minus x plus 2 quantity cubed over 27 plus dot dot dot. It certainly converges at x is equal to negative 2. We will check out convergence by the ratio test and look at the limit as n approaches infinity of the absolute value of negative quantity x plus 2 raised to the n plus 1 over 3 to the n plus 1 times 3 to the n over x plus 2 to the n. And this becomes the limit as n approaches infinity of the absolute value of negative quantity x plus 2 over 3, and we're interested when that is less than 1. We break it up into 2 sections, looking at negative x minus 2 over 3 is less than 1, or negative x minus 2 is less than 3, meaning that x is greater than negative 5. Or x plus 2 over 3 is less than 1, meaning that x plus 2 is less than 3 and x is less than 1. Now we need to check out the endpoints. When x is negative 5, our series is 1 plus 3 over 3 plus 9 over 9 plus 27 over 27 plus dot dot dot, and that fails the nth term test and is divergent. When x is 1, our series is 1 minus 3 over 3 plus 9 over 9 minus 27 over 27, and again that fails the nth term test and is divergent. So our interval of convergence is the open interval negative 5 to 1. We look at polynomials with 3, 4, 5, and 6 terms. And we can see that when we get close to negative 5 and 1, the series are well on the way to diverging. We have spent so much time with series, from Taylor polynomials to all the convergence tests, and now power series and interval of convergence. And yet it's still not clear why we are learning this. And with only 2 more chapters in the manual, time is growing short for an explanation. When we learned Taylor polynomials, we found that we could write sine of x as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot, which is the summation n equals 1 to infinity of x to the 2n minus 1 over 2n minus 1 factorial. Now suppose we wanted the sine of 18 degrees. First, we have to change 18 degrees to radians by multiplying it by pi over 180 degrees. So we are asked really to find the sine of pi over 10. So, sine of 18 degrees can be written as pi over 10 minus pi over 10 cubed over 3 factorial plus pi over 10 to the 5th over 5 factorial minus pi over 18 to the 7th over 7 factorial plus dot dot dot. Only if, though, pi over 10 is within the radius of convergence of summation n equals 1 to infinity of x to the 2n minus 1 over 2n minus 1 factorial. If the radius of convergence r is infinity for our series, then we can plug any number into our series and know that if we use enough terms, we can get as close as we want to the actual value. Even if the radius of convergence is on an interval, then we can plug any number within that interval into our series and know that if we use enough terms, we can get as close as we want to the actual value. And anything outside the radius of convergence will not approximate our answer. So our goal is to find the interval of convergence for these series. In particular, series using functions other than addition, subtraction, multiplication, and division in order to approximate them at any specific value. That is where we are heading in the next 2 videos.